Okay, thank you very much for being here. How many of you heard Chris Dodd's presentation on heat loss? Good part of you. Okay, thank you for coming back. What I'm about to talk to you this morning has absolutely nothing to do with the BC Building Code for heating, for cooling, or ventilation. The whole reasons for asking you to attend this is for a completely different purpose. If we were to ask you to inspect a heating system, I think as an industry, we have a very great responsibility to give you enough of the very simple backgrounds of how a forced air heating and ventilating system work. Because if we give you the background, you're going to get into all these sticky situations on the job site where you've got to make a call. And if you understand the fundamentals of what air is and how you move it, it'll make all those difficult calls so much easier. So this is not directly transferable into Section 932 at all. But I will be using specific examples that I hope will help you. When it comes to inspection of the minimum systems, at TECO we have a ventilation checklist, we have forced air guideline checklist. These are certified individuals, and as I mentioned in one of my comments this morning, we are in the business of suspending certification when it's brought to us and to our attention of repeated, fraudulent, or just plain deliberate attempts to fraud use of our checklist and our stamps. So I think whether we like it or not as an association, as I stand before you here today as president for this year, we as a board are going to have to take more decisive action to the betterment, I think, of our good contractors and to support you, who you to some degree are our eyes for what's happening at the building inspection level. I have about 55 slides, and I have two models that I'd like to show you because I'm a toy type of guy, and I think many of the tradespeople that we talk to are also toy types of guys. That's why they're in the trade. They work with Crestron Edge pair of pliers and a sledgehammer, and we have toys to suit. A very simple toy on your left, and a more complex toy on the right. And the toy on the right is very complex, but we're only going to use it for one specific example to show you the biggest single restrictor to free-flowing air in forced air systems installed in this province. By hands down, it's Solaire. So please feel free to ask any questions at any time. As you probably heard from my noise this morning, I am not easily disturbed or disrupted. We'll just go through some slides, and I will stop when I can best serve your interests. The Principles of Moving Air was a course that we developed about 10 years ago, Gary Milligan and myself. And we developed because we saw a real lack in the basic understanding of what air is and how it moves within our trade. In the 50s, the trades were taught a lot about what is air, how you move it. But in the interprovincial exam now for a sheet metal tradesman, there's very, very little covering design. All sorts of things today which are cladding or making duct, but not the individual aspects of design. And whether we like it or not, the residential heating contractor today has to design and install, because you cannot subcontract the design with any assurance that you can install it, because the frame in reality is so different than the frame that you may see on the architectural plan set, if the frame is even shown. Just so you guys find out that I'm a fairly realistic type of guy. I'm actually a dirt biker. I busted my fingers and toes falling off and all sorts of knee injury. That knee doesn't work very well anymore, but I'm a biker from a long time ago. And that was my first career as a motorcycle mechanic, which put me through UBC in mechanical engineering about 40 years ago. And I joined TELUS, got a really wonderful electrical apprenticeship with TELUS and diesel generators. It was just one of the greatest educational training I've ever had. I've been volunteering with Tech on ventilation for 30 years, and I'm currently president this year, as well as on my day job. I'm actually a partner in Innovative Products. I made this presentation, I don't know how many of you were at the building officials AGM about 3 years ago. I made this presentation with Doug Payton from Kelowna. Is anyone here? Okay, so this will all be new for you. The title at the time was To Avoid Strangling Your Furnace and Help Get Sufficient Air to Distant Bedrooms. That's the sole concern that we've got at Tech in the forced air business. We have to make sure that the appliances that we buy are moving sufficient air to keep them happy and prevent them from failing. But Mrs. Smith doesn't know that so much. Her concern is only that we get sufficient air to her distant bedroom, so we not only heat it in the winter, but we cool it in the summer. And the problem is well, the code does cover this, it covers it in a performance manner. It says you shall heat the room to 22 degrees Fahrenheit, but there's no prescriptive methodology whereby you quickly pass or fail, because that's a performance sentence in a Part 9, which is basically prescriptive how to do this code. I have two comments that I'd like to make that do not reflect the position of the company that pays me, nor that of TECA. And we've talked about environmental issues today, CO2 and everything else. I'd like you to look up in the sky the next time you have a nice clear day, and you see these contrails across the sky. These are toxic as hell. They're put there with the idea of nucleating moisture to reflect solar radiation to diminish the global warming effect. But they're nanoparticles of aluminum, and I guarantee after studying moisture for 40 years, this is not moisture that you used to get from the old prop piston type of engines. These things here, the new engines they use in jets today, 85% of the air that enters this big, huge 12-foot diameter fan wheels goes around the engine, only 15% is burned. And the moisture coming off the tailstock of those engines is so diluted by what we call the bypass air that they will not leave any trail, and they're technically incapable of doing it. These guys are getting a lot sneakier now, and you'll often see these done at 3 o'clock and 4 o'clock in the morning when I go out on a bike ride. But it's really an environmental nightmare, and if you have any interest at all, go to Dane Wigington. He'll blow you away with what's really going on. The mainstream media, nor the weather, will cover. The next one's on a bit of a more positive note. I'd like to introduce my young niece. I don't know if any of you follow the marathon or the triathlon circuit. There was a race in Mexico in Leon. It just finished about a week and a half ago. She was number one. She's the only woman in Canada, only person in Canada that's completed what's called a double-decker. A double-decker continuous means you swim for just under 100K, you bicycle for 3,600, and you run for, I think it's about 800 or whatever K. It's basically here to Toronto, here to Ottawa. And she pulled it off in 26 days straight, and she would have clobbered all the women, except she was food poisoned for a day, she was out of action. But she came in 4th out of 14. She beat all the men except 3 and all the women except 1. I'm just proud as hell of her. Catherine is running TECA. Some of you may know her. She's the small part of the person in the back there. Catherine Tsubasa of our bus. Just the best person in the world you'll ever know. If you have any questions about TECA, call her. She's always available to return calls if she doesn't take them personally herself. We do have industry standards in BC for forced air heating and also for ventilation. But what no one wants to admit is our poorly installed systems are an industry-wide problem. And with modern equipment, the correct design and installation becomes much more important than the efficiency rating of the equipment itself. We have a whole bunch of people today that are provincially and federally funded that are talking about this efficiency and that efficiency. It's all crap. The biggest single thing that determines the efficiency in the light of Mrs. Smith, who's paying with her after-tax dollars for our products, which you are a part of, as am I as a supplier, is the equipment installation, which in the case of heating and ventilating and cooling, the equipment only constitutes about 20, maybe 25% of what Mrs. Smith pays. The wild card is that which we completely ignore, and that is installation in the building, and I will use specific examples to leave you scarred for life. What I'm talking about right now is the principles of moving air. It's a complement of 7 things that we offer at TECA. We continue to grow it. We've had massive capital investment here this last year, and it's starting to gain some traction because I think there's a widespread acceptance today that mechanically we have to do better. The course that I'm condensing right now is a 2-hour course that's aimed specifically at the sheet metal trade because we knew there was some problems there. But we decided to try run it at one of the premier conferences in all of the United States, which is hosted by Joe Stieber. It's an invitation only. It's in Westford, Massachusetts. And it's called the Westford Building Symposium. There's 480 people there. And this received first-class recommendations in both 2015 and a replay of 2017. In the United States, they're even further behind in this area than we are here. And it's really a sad state of affairs. Basically, I'm going to talk about 2 things. Happy equipment means we have to give equipment reliability, which means we've got to flow adequate air through it. What happens if you put cardboard in the front of your rad and try to drive around in the summertime? Good luck. You boil it over. You cook your engine if you're not smart and shut it off. Well, that's what we're doing with our duct systems right now. We're putting cardboard in front of them. We're not allowing them to take the heat off as they should be. The second thing, Mrs. Smith doesn't know about that so much, although a restricted ductwork system generally is noisy. Her concern is that we're getting enough air to each habitable room, and that she's right pissed if we don't give adequate heat or adequate cooling to the bedrooms, and they're one of the greater challenges today because they're most distant from the appliance, with so many of these appliances now in basements when the attics are now essentially verboten, unless you spend some serious money and condition the attic, which is not yet, and I'm not sure it ever will be commonplace. So the question is, how do we accomplish this? If we break the rules, we get excessive noise, we get short filter life. It's not commonly understood, but if your system right now is put in a marginal configuration so that the furnace is just able to meet the requirements for moving air through it, and you put a filter in, that's bad enough. But that filter may have very, very, very short life before. The filter is still fine, but it's pushed the system over the edge to where you're now starving that equipment. So your filter life will be very, very, very short if you have a restricted ductwork system, and the filter just becomes an added piece of straw on the camel's back to actually break the camel. For heat pump, what's not commonly known, and I'll get into it at length, heat pumps are air-sensitive equipment, and a lack of airflow puts your compressor at risk. And the compressor is the biggest single cost component of a heat pump. And when that compressor cooks, it often contaminates the system with the refrigerant being contaminated with all sorts of garbage from the compressor. And unless you spend very expensive purge and system purge that contamination, you may cook the next one. You cannot ever, 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 ever cheat on airflow through a heat pump. In a gas furnace, if we starve them, we tend to have a higher exhaust temperature, which means we cook the venter motor prematurely. And what you may not understand, because our industry has been sold the be-all and end-all of efficient gas furnaces to put in the $1,000 electronic motor, and they're beautiful. In fact, GE's patents just ran out here recently, but they had the market for 17 years producing what we call ECMs, and they're extremely energy efficient. The beauty of them, though, is they are smart enough. They have a brain. It's an ordinary motor, but it's got a brain on the back end of it. And that brain says if there's a starvation for air, it ramps up. There's two things wrong with that. As it ramps up, it satisfies the air requirements through the furnace. The problem is what happens is that it consumes a vast quantity of electricity, so all the savings that you could potentially get, many of that is lost through this motor working harder through a restricted system. What I've also heard of recently, though, is a number of these things now are failing because they're pushing against restricted systems, trying hard to bring out an attempt. And it's anywhere from $1,000 to $1,500 at the retail level to replace one of these so-called efficient motors. So that's where I'm coming from as a background to why this is really important, not only for you as homeowners, but also for you in your professional capacity. As a part of developing this course, 10 years ago, we spent $5,000 and we built a miniature furnace. Our philosophy is not to spend money on an overhead in an office, but rather to keep all of our training portable so we can take it where you want us to take it. And we'll produce training anywhere you want in the province on a demand basis. So this all fits into a box that you see underneath the table, and it allows us to be able to demonstrate in a hands-on configuration to the tradesman exactly how air moves in the duct. And this will be the second model that I will show you today to leave something that I hope will be sticking with you for the rest of your life. It all begins with a lowly cubic foot. Now, this cubic foot has no weight. It has mass, but it doesn't have weight because it's being buoyed up by all the air around us. But every last cubic foot weighs about 1/10 of a pound. So I'd like to take this now and I'd like to translate this into what really happens in the duct system in a rather horrific way. If you were to take that stone slinger and have the stone slung right into the basement, if you had an apprentice there with a wheelbarrow and he was able to take 200 pounds of stones every minute and perfectly distribute this to all the rooms of that house in balance of the need of that room to match heat loss, in other words, the weight of stones to do the job, your apprentice would last 5 minutes and he'd tell you to screw off and you'd go out the door. This is what's happening in the real world with the heating system right now. We think of air as having no viscosity. We think of it having as no mass, But in fact it does, and it takes a lot of energy to move air, and we have to start thinking fresh. And I'll support that with the next few slides. These fans do a lot of work. Now, how many of you people have furnaces in your house that may be 30 years old, 20 years old? Yeah, good number of you. These older furnaces were literally built like the proverbial, brick, what. And these things ran at a fairly warm temperature, which kept their heat exchanger dry. And the air coil, which was manufactured here in Mitchell Island, these things will last 30, 40 years with unbelievable reliability. Just beautiful piece of machinery. Stupidly simple. 80% efficient, which is damn good compared to your car at 30%. And it was a really fine piece of machinery. Well, if you stood on the forced air grill on your bedroom after the furnace has been running a while, that grill is going to be about 160 degrees Fahrenheit. And that's where that furnace wants to operate. That's its sweet spot. So for purposes of comparison, we're comparing 70 to 90 degrees, which is the green band for those older furnaces, to electric furnaces which run at cooler temperatures. The new gas furnaces run lower again, and look where the heat pumps are. They run at a very, very, very cool temperature, which is why if you're a tradesman and you install a heat pump into a retired person's home, be prepared for the flak. This is air conditioning my house in the winter, it's not heating, because they've come from a 160 degrees Fahrenheit delivery temperature to maybe 100 degrees temperature, which is doggone near their body temperature. With the wind chill effect, it actually feels like you're air conditioning the house in the winter while your heat pump is at full capacity. I'd like to take this information and turn it inside out to where it's relevant to duct sizing and design. On the left-hand side today, if I can make this work, is the old gas furnace, and this air has a huge amount of punch to it. It's because for 1,000 BTUs, you can get away with about 12 cubic feet. And just for fun, a 4-inch duct will handle 40, so you can handle 3,000 BTUs really, really easily with a 4-inch duct. But if I take the opposite extreme and use a heat pump, it takes now about 3 times more air to do the same job. So anyone today who takes out an air coil and puts in a heat pump and matches the BTUs is an idiot, because you'll destroy the compressor. And people might contest these kind of outrageous statements, but you can't fudge physics. I dropped one on the provincial government right now because they're trying to launch a heat pump program, and I think they've got rocks in their head. But I said, you can ignore reality. You can ignore reality if you have enough money behind you. But you cannot ignore the results of reality. The simple fact of life is if you put a heat pump into the older duct systems and you match the output of what you had with a heat pump of the same capacity, you will destroy them. It's not politically nice to say these things, but I'm getting old and ugly, and I really have nothing to lose at my age right now because I finally reached pensionable age, and that's kind of nice. Besides, you guys haven't thrown me out yet, and that's sort of my measure of success or failure. If you kick my ass out of here, I won't come back. Well, Gary Milligan is doing something which every last furnace installation requires that you do, and that is do a temperature rise. It's not being done. But the condition of the approval by CGA of that gas furnace requires the manufacturer in the manual say that the installer shall do a temperature rise and clock the gas meter to make sure that that thing is burning correctly. So, what does he do? He's putting a thermometer here in the cold air return, which is the air coming from the living room, and that's going to be about 72 degrees Fahrenheit. And you may ask why I speak in metric and the code speaks in English, or vice versa. It's because our industry is dominated by the US, everything we do is in English, and if you want to reach the trade, use the trade language, it's a common courtesy. On the supply side, of course, this thermometer gets taken out of here and puts in the supply side. And the difference is the amount of heat, the temperature rise that that appliance does when it's operating sweetly. It's a very simple procedure. It's very, very fast, but it's never done. And yet it's a requirement as a minimum installation standard. And the other thing Gary's doing is using a clip-on ammeter to measure indirectly the power consumption of the motor that's used to circulate the air. I'd like to zero in on this return air drop because a good part of my discussion and this model is going to be focusing on that return air drop because that's the biggest villain that we face today in this province absolutely universally throughout all gas, forced air, and heat pump systems installed in this province. I'd like to go back in history with some absolutely dead-on catalog examples. There's two furnaces on the left. One furnace is a black one is an outline in red. The black one is the air cool. As you can see, it's 57 inches high. The red outline, which is surrounding the black one, represents a brand new Lennox furnace. We chose Lennox only because Gary's a Lennox dealer. We got the data real easy. And you can see that that furnace right now is 33 inches high. There's huge pressure on manufacturers to shrink appliances, but that's backfiring, and here's why. If I took a look at the air cool, oh shit. Okay, you take a look at the air cool, and it was 80% efficient, which is pretty damn respectable. You know, wood's 50%, coal is probably 30%. You know, that's pretty darn good. And its output, which means the amount of heat that this produces into the house for Mrs. Smith, is 68,000 BTUs. And of course, its input's a little higher because there's a 20% waste in the process. But the thing that's important for this discussion is that circulating fan would move 730 of those cubic feet, which means 73 pounds per minute. And it would do this at what's called an external static pressure of 0.15, which won't mean squat to you. The reason that number is very important is because this appliance was developed shortly after we left the gravity forced air systems, where the ducts were very big and everything ran by convection currents. So the first furnaces built were running at very low static pressures with very small motors because we had a trade practice of gravity systems, and our ducts by and large in the 50s were actually quite a bit better done than we do today. But that's not the problem. What I'd like to do is you compare it with the Lennox today. And this is no reflection, good or bad on Lennox. All these appliances right now manufacturers have a gun to their head to get the best efficiency, because that's the game in town right now. It's all crap because the installation is the issue, but the nameplate rating is what drives manufacturers today. So of course they get 95%. Well, how do they do it? Well, they don't tell you how to do it. What they do is three things. Number one, they produce a frigging big fan in. Because the only way to cool something really, really, really well is to move a massive amount of air across it. And that's number one game. Number two, you put bigger heat exchangers inside. There's more surface area. It's sort of like putting a big rad in your car if you're using it in the sand dunes, so you get better cooling. So that's number two. I forgot number three. The net result, however, is that from the installer's point of view, is that we have 1,257 cubic feet a minute, or 72% increase in airflow in order to make that appliance run in the sweet spot. The next picture, though, is even worse. A 72% increase in airflow. That appliance was supposed to operate at 0.3, and we're running at 200%, more than 200% over what it was at the very start. But look what happened to our motor power. The original was doing just fine with the 1.6 horse. Now it takes just under 1 horsepower to do the job. I don't know if you guys know anything about electrical rates, but just for fun, I mean, this doesn't run full time. But do you know what 1 horsepower costs on second tier rates right now, running 24/7? It's $1,000 a year. You're not going to run full time, but just to put the scale in here, 1 horse is $1,000. That's power delivered with all the frigging levies and taxes and shit when it gets to your bill at home in the mail. $1,000. Okay. I'd like to do a small fan demo as a very, very, very basic introduction to air. We developed this at Tech about 20 years ago, and we thought it might have a 1-year life expectancy. But even today, when I bring this out to the trade, the guys just drop dead when they see the results of this simple demo. So I don't know if you guys at the back want to walk up, but it's going to take me about 5 minutes to run this demo. If you're curious about it, I'll leave you lots of time to get back to your seat, and I'd welcome you standing up if you want to see it, if you haven't already. For those of you who are not moving, we have a fan on a table. We have 2 gauges. The gauge on the left is reading how much, what we call static pressure. In other words, that's how much pressure the fan has to build up in the duct in order to move air through the duct. Because with fans, you cannot move air through the duct unless you've got more pressure at one point in the duct than somewhere else. So the left-hand gauge actually measures how hard the fan is pushing as measured in what we call inches of static pressure. The gauge on the right is measuring flow. So what we're going to do is we're going to show you two conditions that are very simple. What happens when I put my hand over the duct, which is, we have a special word for that, it's called a shut-off condition. In the real world, that means if a bird builds its nest in your bath fan outlet, or the grill lids over, or in the case of a forced air heating system, if you pull out the air filter and it looks like a piece of cardboard, you have what are called shut-off conditions. So we can demonstrate that quite easily. Okay, this gauge here is reading about half scale, and it's measuring the pressure that it takes for this fan, static pressure, to be able to carry the air, move the air from this fan point here to the end of the duct. Even though the duct is straight and it's short, there's no free lunch. Air will not move in a duct unless there's a force behind it. And the force behind it is measured in inches of water column. Technically, it's called ESP, external static pressure. Okay. The gauge on the right is sitting at about mid-scale right now. If I were to put my hand across the end of this, I don't know how I can do this. If I put my hand across the end, for those of you at the front, you can see this gauge actually went to 0. Because, of course, the airflow went to 0. It's a totally unrealistic situation. Now, this gauge here, when I put my hand across it, it reaches the highest point, and this is shut-off condition because the fan is winding up and winding up. That noise you hear is the increase in RPM as it's trying to push against a deadhead, and the net result is it goes to what we call shut-off pressure. So these are the two conditions that this fan would see in the range of operation. This is why in the ventilation code now there's a requirement of how big your duct has to be for a certain size fan at a certain distance, because it's showing that if you want to run duct 50 feet, your duct has to be bigger than if you run it straight from the ensuite directly to the outside wall through a hood. Okay, now there's a whole bunch of conditions inside this parameter of shut-off to full flow condition.
One quick question. Could we just re-clarify where those two sensors are reading from when you did that?
Sure.
Yeah.
The left-hand gauge is measuring external static pressure.
Yeah.
There's a drill hole in the side of this duct,
and
this piece of brake line is silver soldered into it, so it's just seeing a hole in the side of the duct. It's measuring the bursting pressure of the duct. It's not measuring the velocity effect going through, but only the static pressure. So if you looked inside this, all you'd see is a flush surface with a hole.
Sure.
And the tube just means I can hold this on without having to physically hold it.
Yeah.
Now, this gauge over here is measuring flow. And for those of you who know fluid dynamics, you can measure flow a number of ways. The pitot tube is what airplane pilots use and what you'd use in a commercial system. What we've used here is an iris, which closes down and it measures the pressure one side to the other, which is indicative of the flow through the device. So, external static pressure, and it's directly reading cubic feet per minute, although it's scaled. So what I'd like to do is show you a couple things to show you that every last thing that we put on this has a direct effect on the ability of the fan to move air. Now, contrary to popular belief, the standard bath fan doesn't care what you do with the duct. In fact, if I restrict it with whatever means that I have available, even something like this, the fan will wind up a little bit, although not much because it leaks around the edge so much. But if I block it, it will wind up. And the fan actually is using less power. Does anyone want to hazard a guess why when it's blocked it uses less power? It's not doing any work. It's not moving air from point A to point B, so it's actually just windmilling like a stupid chipmunk. So there's no power consumption. The fan's happy. This is not a smart fan. This is not a compensating fan. It's a PSC or shaded pole motor. Okay, what I'd like to do without the mic and try not to block the camera is I'm going to show a few things of what happened here. So, I can put an elbow on this fan, and right now, I think you can see the result. Our flow went down a little bit, our pressure went up a little bit. The fan is developing higher pressure in order to overcome that. And this is just a simple elbow. I could put 2 elbows on it. It's all additive. But these aren't the boo-boos. These aren't the bad things you see in your world. I could be a real idiot and spend $20 to make a right angle elbow, which is no reality in the small duct business, and put it on. And it has a greater restrictive effect than does something with a radius for common sense reasons. This is one of the best designed hoods that you can have on the outside of a building. These things free flow quite well. But it will have an effect that is measurable. The sheet metal ducts are not quite as good. These hoods are not quite as good in aerodynamic shape because with plastic you have almost unlimited freedom at the mold design stage, which you have limitations when you're doing a sheet metal hood. This is one of my favorites. This is what most of you probably enjoy if you have a bath fan that was installed about 20 years ago, because only around 1987 we started with the hammer to bath fan ducting for obvious reasons. And if you've got 3-inch duct, you're probably going to have 6, 10, 20, 30 feet of it outside. This is a bit of a dated example. I love this one. Straight through, everything looks just great. That's not how the air sees it. And yet, how many of these have you seen in soffits with a piece of 6-inch, 5-inch, or 4-inch duct elbow turning directly into a soffit with a screw on the bottom of the soffit? So for getting a hassle of some of that air going back up and rotting the attic out, which is more of an issue today than when we had warmer attics, but this thing here just absolutely cripples the fan. So without being scientific, if you were to stand in your bathroom, how do you know if your bathroom fan's working? The typical answer, of course, is toilet paper and a fan, but what is the better answer? It's a completely simple, stupid answer that I would use for myself. You get out of the shower, your feet are soaking wet, and stand beside the door when it's closed, and if your feet freeze, it means your bath fan's sucking air like stink because it's stealing it from the house, is passing your feet and going into the fan, so you can measure your bath fan performance with wet feet. Okay, so I will go later in this a little heavier, but I'd like to get into some more background. So if you grab a chair, we'll go into this a few more slides, and then we'll come back to the larger scale model. Very simple.
Does the same concept work when the fan is drawn?
Thank you. I'll answer that question.
Oh, okay.
The question came up, does it matter whether I push air through or pull air through a duct? Does it make any difference? I won't get into the physics behind it, but the answer is an absolute, unequivocal no. If I'm pushing air through this duct, it's a 4-inch elbow, and whether I pull air through this duct, the restriction imposed by this duct at that air volume will be unaffected, or whether the fan is here pulling or the fan is here pushing, it doesn't care. We do know that this fitting imposes far greater pressure drop, or what we call, what's the proper term? It's restriction to the air just because it's an undesirable geometric shape. Okay, so now where are we? You now know all about fans, and you know that if you restrict the fan, its performance goes down. And these are the workhorse fans out there today. Some of the newer, really expensive ones are compensating, but the majority out there are not. Okay, now to put some more perspective on things. You may not know it, but in our business we have speed limits, and they're not violatable. Just to put things in perspective, in the case of a trunk duct, which is a big one beside the furnace, we can't go more than 1,000 feet per minute, which of course doesn't mean squat to you, but if we put it in miles per hour, we can't go more than 12 miles an hour. Which means to say that we have a speed limit in our duct systems, and the biggest ducts, which the air goes fastest, is less than what you're allowed to do in a school speed limit. The branch duct, which of course is closer to Mrs. Smith's bedroom, has to be a lot smaller because it's where the sound is more critical on the part of the consumer. But there's another scientific reason, and that is the smaller your duct is, the more metal you need for the same square inches, so that the friction effects on smaller ducts are drastically larger than the friction effects on ducts that are larger. So larger ducts always win against smaller ducts in terms of efficiency per square inch. This is the workhorse that does every last job for this province for heating and cooling and some ventilator systems. It's what we call a forward curved fan, which means it collects dust, which is one of its hassles, but it grabs air with its forward curved blade and centrifugally throws it and spits it out one end. And we call them double inlet because it's got an air opening at either end. And as you can see right now, the air enters this side of the fan unrestricted, but this side is blocked by half of its area with the motor, which is lousy design from the point of view of airflow, but it's extremely good because it's inexpensive and because the motor gets really good cooling. I'd like to give a case example right now that just became just outright ignorance and fraud, and I'm not sure which trumped it. I was wearing my own company hat, Energy Products, when I was in West Vancouver. Oh shit, I shouldn't have mentioned that. Anyone here from West Vancouver? I guess I won't toast myself this time. This system was being installed. I was looking at the ventilation system, and I found there was an air conditioning piece of equipment going into the same mechanical room, so I was certainly concerned from the point of view of the ventilation that the space was not compromised to where the ventilation would not work. And I learned from the builder, just casual conversation, that there was a 5-ton air conditioning system going into this house, which may or may not have been needed. That's not the point in question. Now, a 5-ton air conditioning system needs to circulate 2,000 cubic feet a minute, which is 200 pounds a minute. But the horrible thing was, on a quick measurement of the supply duct, which had been roughed into that mechanical room, the duct was only capable of 2 tons, 800 cubic feet a minute. It's just, I don't know whether it's fraud, stupidity, whatever, but here we got our multi-million-dollar lot, a multi-million-dollar house, and air conditioning system. At this stage, you can see it would not have a hope in hell of working, regardless of this bullshit terminology called commissioning that everyone thinks is going to be the savior. And if we go back to very simple tables, Quality First has tables. They're just beautiful. I use this table every day for 25 years. It shows in a very simple duct system, which means there's 3 to 4 turns. So it's a very simple system. The ductwork was there, was capable of somewhere between 760 and 860 cubic feet. What's needed to do the job had to be right up here, minimum, but it really should have been up here around 2,000. So I made a boo-boo in that line position. But the net result is that the duct that was there was half that of what was needed to do the job. Now, some of you may have enough experience. What's the immediate result if you restrict the duct on an air conditioning system? If you don't have enough air through the coil, what happens? The coil gets colder and colder and colder. The compressor works harder and harder and harder. But what happens? All the moisture ends up freezing up that coil, and the thing there sits there until it shuts down. Hopefully, because it's got shutdowns. Your worst case scenarios where there's no shutdowns, the compressor will destroy itself. You can only do that for so long before it's had enough. I'd like to go back, and it sort of brings to mind the actual history of this whole course. What I'm about to talk about, or what I have talked about and will continue to talk about, this was all known way back in 1930. Believe it or not, every last piece of information in this manual can be found verbatim in 1930s documents from ASHV, which is the predecessor of the ASHRAE Association. At the time, they did not have neat technology we have today, so this image was actually taken with a plexiglass duct and putting little wee soap bubbles into an airstream and using a strobe photograph. And what happens is, going back to the picture with Gary Milligan, as the air is coming down from the cold air returns in the floor above, it's nice and straight at this point because it's had 6 feet from the ceiling to straighten out and become what we call streamlined. But what happens is the air overshoots this sharp throat, and all these little wee vortices right now mean to say that the only air that's actually leaving the bottom of this right angle turn is the bottom 1/3. How many of you people have what we call high boy or upright furnaces in your house now running a gas? Do you have filters that are mounted right next to the side of the appliance? 99% of you will. Have you ever pulled the filter out and look at how the air is distributed, the dust is distributed across the face of the filter? Next time you do, look for it and you'll find that the bottom 1/3 will be filthy, and the only time the 2/3 of the top becomes dirty is when the bottom is so bad no air can go through it, and the air will start to curl up and go through the upper half, the upper third. The bottom line is these systems are destined to fail from the moment they're installed, because what we've done is we put in a fitting, which I've called a pig, is absolutely killing the performance of that system. And if we were to single out any single part of the whole ductwork system in terms of restrictions occurring with this one single fitting. We now can put some science to it. We spent $150 for a CD from Ashray and SmackNet. We spent about, I think it's about $5,000, and we converted it all to simple charts for the trade. And what we can tell you now, beyond a shadow of a doubt, if you have a duct that's 8 by 32 or even 8 by 20, doesn't really matter, at the bottom of your furnace, going into your furnace into the filter, that duct has an equivalent pressure drop of 50 straight feet of duct. In other words, one lousy corner has become a huge penalty, and the air thinks it's gone through the equivalent of 50 feet of distance. I mean, it's just frigging nuts. For a lousy turning vane, $100, $200, you can knock that to $6. Because what you've done is you've overcome the sins of all those sharp throats by providing a turning vane to ease the air around it. But it's actually far, far, far more subtle than that, because by doing that now you're putting the air uniformly across the face of the filter, which would not have occurred had those turning vanes not be there. So the pressure drop through the filter is about 1/3. The pressure drop through the fitting is about 88% less with the turning vanes than it was pre-existing. But if any of you have looked at heating systems recently, you might think that the upgrade is the radius heel, which is the upgrade that standard sold fitting in the wholesalers today thought to be an upgrade, but in fact it is a worser fitting than that, which is the low-end sharp throat, sharp heel, which I pictured here. So what is perceived by the trade to be better, in fact, is worse, but I won't get into that. Now, we've also got a bit of a fetish right now for filters. Mrs. Smith is thinking, gosh darn, 3M and a bunch of other companies got big bucks behind promoting really good filters. Awesome, filters are good. Because what we can do now is we can do a lot better than just protect the equipment. What we used to do is just have a good enough filter in there that stopped the fan from gobbling up really, really big stuff that hurt it. But now we can put in filters that are reasonably economic, basically $10, $50, $120, $30. We can put in good filters right now that actually improve our respiratory systems by taking out the particles which we would have otherwise inhaled. The stuff that's so small it doesn't settle, the stuff that stays in the air until we breathe it. The problem is today, these are being sold right now on a MERV basis only, with zero concern for the restriction that they impose in the heating system. So if you are starting to use filters like this, it's really, really critical that you take out the resistance in all their aspects of the system, so you have enough air power left over to overcome that, which generates a benefit for Mrs. Smith. None of this shit's in the code, but we've got to start thinking smarter. We really do, because we're crippling equipment today. Just a case study that was kind of fun. Clean filter, dirty filter. Here's one that's subtle as hell. Clean filter on the left, believe it or not, the filter on the right is totally dead. And it doesn't look too bad. If you look at it very, very closely, you can see there's a bit of dirt in it. But what happened is that filter on the right was pre-filtered with the big stuff. So it lasted 5 years, but it totally suffocated the appliance. So you can't no longer measure filter performance now just visually. You have to have a routine change out, or you ideally have to measure pressures. This one here just looks absolutely gross. It's a 2-inch pleat filter, and the pleats are absolutely loaded to the full 2 inches depth, and it still flows air, because it was in a pre-filter configuration right now, and the particles are not small, they're big, it's filled it up quite quickly, but it still flows air, and yet you think this was overdue for a change, 5 years ago. Another case study here that I love, and this was personal, and I was pissed. My sister just moved to Bridge Lake, which is just a little east of 100 Mile House. It's 4,000 feet of elevation, and she came from Rosedale. I said, you know, you're moving to where your energy costs you 3 times, your climate's twice as much, you multiply those 2 together, and I said, if you're not careful, you're going to get whacked with a heating bill. It's going to choke your horse. In fact, she'll have to sell her horse to heat the damn house. She'd never do that. Anyway, I suggested to her she get a cold water heat pump, and the builder got her a cold water heat pump because he basically had a gun to his head. That was a condition of contract. But he hired someone who's a complete idiot to put it in. I took one look at that, and I decided, well, something's not very good here. So I said, in my most diplomatic point to the builder, what was wrong, and he suggested I call the trade. I called the trade, which I will not name unless I screw up and release it. I said, you know, humor me, just take a static on the return, take a static on the supply, and tell me what you got, because my suspicions are this isn't going to fly. Well, of course, I got 10 minutes of absolute harangue for this, of defensive position. As careful as I was, it just blew up, and I figured this ain't going nowhere. So I called up the supplier of that province, that particular product, and I said, you know, we got a serious boo-boo here. I don't think this thing's going to work. I think it's going to blow up. Next time I went to visit there, I found out later by the back channels that there was between $1,000 and $2,000 worth of duct changes. And finally, surprisingly enough, the equipment had been reinstalled up on a bottom return, and actually was installed to meet the manufacturer's minimum requirements that were in the installation manual that were in front of the contractor all along. Here's a case of complete underqualified person who didn't care, wasn't willing to learn or listen, and that thing would have blown up because these things take a hell of a lot of air to move air adequately through them when it's 20 below or 15 below, and these things will still actually perform. This thing is amazing. It goes right down to 15 easily, carries the whole doggone house. You're using wood in the few coldest days of the year, but this thing will carry the house all year. It's quite an amazing machine. Here's an example of a splitter, which is even more sophisticated than a turning vane, because the vane actually starts right here and it goes all the way through. You can see the little spot welds here. It's guaranteeing that the air proceeds in a perfectly streamlined pattern into that filter. It has to be. It's non-negotiable. If you guys would like to get up again, I would like to show you one thing in this model that I think will solidify in your mind the validity of the single fitting being the culprit that I've tried to convince you that it is. So this will take about 5 minutes. You can sit down, stand up, whatever you like to do. Any questions so far on any of this stuff? I'm sure it's coming out of left field for most of you.
Would you put turning vanes everywhere you have a 90 in the main duct trunk runs?
If you had more money than brains, yes. The whole idea of a contractor, and Gary is a contractor through and through and through and through, he won't spend a penny unless it's justifiable to do. And what he's learned is all the money for flow through the appliance has to be done within the first 10 feet where all the air is going through the one duct.
Well, okay.
When you get into branches, it's a waste of time because your speeds are lower and you're not getting nearly the financial benefit as you are when you're within the first 10 feet.
Good.
Okay, this here is a furnace in miniature. It's blowing air through this supply air duct, which is horizontal, and that way we don't have to worry about falling over. And this is the drop from the ceiling return air plano. So this represents the drop of a normal house. And in this case, it's turning into the end of the equipment. Normally, it would turn into the side. For illustration purposes, we have it come into the end. What I'd like to do is I want to run this thing wild right now with no restrictions at all. It's a reasonable approximation of reality. I'm going to plug it in. And this gauge here is going to measure how much pressure, static pressure, restriction, the measure of restriction between this, which we know is streamlined air from that old 1930s photograph, into the return air compartment of that fan. In other words, this is the static pressure this fan must overcome to make this one corner. And we do not have a filter put into that because it just makes this situation even more complex. But for the trade, we actually have a filter we can put in, but I think I must have left it in the box. So what I'm going to do is I'm going to turn it on. Over here, I have 2 tubes that are connected to this gauge here, and this is going to measure the air volume that's going through it. So in my starting condition, I'm going to run this through here, and then I'm going to change this fitting, which we know is one of the worst, and I think I did mention This is what a lot of the trade thinks is an upgrade, but in fact it's worser than this sharp heel. And I won't get into the physics of it, but this test shows that this device here, which is thought to be an upgrade, is in fact a higher static pressure drop than the real low end. Cut the side of the duct and screw it to the furnace. What I will do is I will show you, if money was no option and you wanted to spend one single dollar on one fitting, you'd radius the throat, radius the heel, put a turning vane in it, and I'd like to show you in a way that I hope will convince you of what we do today and what we should be doing, especially on the move towards high efficiency appliances and towards heat pumps. So I'll turn this on, and this gauge is going to measure the airflow that's going through that. So just for fun, you can see this is just sitting a little bit with 0.4. So forget about that. We have tables to convert that to CFM, but that's not relevant for the moment. Over here, I'm showing that we have roughly 0.3 of an inch of static pressure, which, by the way, is the total system allowance for a whole gas forced air system. You're supposed to be running at 0.3 plus the allowance for the filter. So my entire 0.3 allowance for my gas furnace has been consumed in one change of direction. So what I'd like to do is I'm going to take this guy off and put this guy on, and I'd like to measure the difference that occurs. But to do that, I will have to damper this down to bring my flow to the condition in which I started, so I'm not mixing tests here to screw up your heads. Okay, so while I'm doing this, if you've got any questions, fire away. You might wonder why these stupid little things are here. Air does not like to enter a sharp edge of a duct. A commercial heating contractor will always have a grill that's 50% bigger than the duct opening. This allows the air to come in straight, which gives me stable readings. If I do crazy things, it bounces around and I don't get meaningful results. So this makes things a little bit better. Toys are fun. My second life is going to come back as a machinist. I really enjoy it. Okay, this is what we know from academic perspectives and fluid dynamics. This is the most favorable one. So what we'll do is we'll pop this back up. That way we're feeding it the same air, for good or for bad, that was there before. And we'll turn it on. And the flow rate, of course, is going to be quite a bit higher. A little bit, not much. I'm going to damper this down now. I think it was something around 38 or so. Is that about where it was? Just below 0.4. Okay, give or take for the likes of you and me, we have now replicated the flow through this system exactly as it was before, and look what we've done here. We have absolutely no measurable pressure difference between here and here because we've made a turn that is aerodynamically clean. So what we've done is released all this pressure that we were wasting before, dollars and dollars and dollars per year with that one single fitting. The system will be quieter. This will not generate any noise because noise is the byproduct of turbulence and pressure drop and wasted electricity. So essentially we made a corner now, a little bit more space used because what we had here before, we ended up with a little bit more space used, another inch or so, 2 inches. But the net result is we have a system now that we could put a filter in now, so we've released so much static pressure that we're completely wasting through this. And the further, this does not take into consideration the double whammy effect of the fact that the air going through this filter now is uniform. And when you buy a filter, if you study the small print, the pressure drop through the filter, how do you think the filter manufacturers are going to rate the pressure drop? With uniform velocity across its full face. Because they have to. Because anyone's going to be an idiot if they only use 1/3 of the filter when they bought 24 by 24 and they use the bottom 8 inches. Any questions in this model? I mean, we could make this thing dance for 4 hours. but I'm hoping that I can focus your attention on one single thing.
Is that type of elbow in the installation manual for furnace products?
Most of the larger furnaces today, in their manuals, require bottom return
Right.
as a way of trying to reduce the speed at the point where air enters the appliance. What you may not know is, if I look in this fan, I can see a fan wheel. On the other side, I got a motor. If my drop comes down on the side the motor happens to be on, and I'm going straight into that furnace, on the motor side, with this fitting and a filter here, I've got the worst of the worst of the worst, but that's standard practice. Our industry has some problems, and we desperately need your help because you are the authority having jurisdiction, and we'll do anything we can to help you feel more confident of coming down like a ton of bricks on people that aren't competent. But the reason for this is not to go into the code sentence by sentence and to give you a fundamental background of what air is, because you have to know that to have the confidence to go out and point fingers at stuff that's just conspicuously inadequate. Any other questions?
I don't know. You were to oversize the return. Would that be
You can
better? Or
always
make a difference?
overcome sins by going big, because your speeds slow down and the lousy geometry doesn't matter if you go big. But generally speaking, we're asked to put things in such a small footprint. We're playing all the games we can to go to minimum, and then all of this sophistication becomes critical because we don't have the space to spread out. Now, you look at the complication factor now of using appliances that move more air, heat pumps the most of all, putting them into a shoehorn, and then expecting them not to blow up and generate efficiency it's pissing in a windstorm. It's not going to go anywhere. To give you an example, right now one of the larger wholesalers of heat pumps, which is EMCO in BC, they sell American Standard. They have a deal with American Standard, which of course is Train, they're manufactured in Tyler, Texas. If that compressor blows up, it's immediately FedExed to Tyler, Texas, and Tyler's promised 2-day response, warrant or no warrant. If it's gone down on high refrigerant pressures, which is a direct result of restricted ductwork, the warrant is rejected. The installer pays. If it's a manufacturing defect, they'll immediately credit EMCO, which will credit the contractor. But EMCO and Train, American Standard, said, enough is enough, we're not paying any more for this shit. You guys blow it up, you pay for it. And I think you're going to find, in the competitive world right now of low margins, that philosophy will creep through the whole business. But I know in the case of my sister's house, that manufacturer had a huge commercial interest in holding that installer with a gun to their head. You fix that shit. Any other questions on any aspect of this? The issue today is no longer the appliance. The standards have come to the point right now. It doesn't matter whether you're 92, 93, 94%. It's pissing in a windstorm. The issue is install, 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 install. Junie, I'd sure love to have you rewrite 933 and build some of this shit into it. Wouldn't that be wonderful? Who do we have to shoot to make that happen? Junie's from Policy Branch. We've been working with him for years on ventilation. He's got his act together. Okay, any other questions? Okay, sit down.
That thing that you showed, I think you could do Absolutely.
Which company?
Feeling.
Yes, Phalanx.
Yes.
That's a class act. And his kid Harry?
Yes, but Harry's gone.
I know, he died.
Yeah.
It was cancer of some sort.
Yeah, but it was funny because the old guy and Harry actually, I've got a log house and I use an outdoor wood burner. The second is water through a radiator in the furnace.
Forced air indoors.
And then forced air indoors. It was really interesting.
There were still some good people. Okay, so we've now decided, or I shouldn't say that, we've now given a brief introduction to what keeps the equipment happy from the point of view of efficiency, longevity, and everything to do with that. We have a completely separate, so forget everything I said right now. We're going to turn the table completely and look at things from the point of view of Mrs. Smith. We have a big problem right now serving Mrs. Smith because, of course, we have houses today on the main level in which we have no partition walls. You can't go up an outside wall. We're really kind of screwed. How are you going to get the heat in the basement to reach Mrs. Smith's bedroom, without designer duct, which is, plexiglass and goes through the middle of the living room? Anyway, Gary Milligan and I were crying the blues in Kimberley here a few years ago, and we went and talked with your CEO, Richard, here some years ago. Really good, level-headed guy. I have a lot of respect for him. He put us in touch with HPO, and we took a look at things. The fundamental issue is we have no inside wall space, can't use outside walls. The branch ducts going to Mrs. Smith's bedroom are too small, they're too friggin' long, too many fittings, which is a sophisticated word for change of direction. Every time air changes direction, it doesn't like that. That's why there's a difference when you have to change direction, whether you have something that's harsh or something that is very good. We can't put equipment in the attic, and by and large, the equipment doesn't care. The equipment only cares about the duct within 10 feet of it. Mrs. Smith is a whole different ballgame. So we put together a bunch of guys. Unlike most committees that do stuff, we got the tradesmen involved. The guys that are actually qualified to find out what the hell's going on. But for reasons of professional etiquette, with Don McAdam, who's got fluid dynamics prof at UBC, and Loris, the professional engineer, he ran Echo Manufacturing. So this is done above the board at the highest academic standards, although it was directed by the trade. It was not. Thank you very much. Don't hesitate to speak up. Okay, thank you very much. This was directed by the trade and not by the guys with the credentials. Now here's something you may not know. You've all seen Echo sheet metal duct, and it has the size stamped on it. 6-inch duct, 3x10. The 6-inch duct has got 6-inch written on it. This is an oval, 5-inch, and this. But what you don't know is that the round duct has got 6-inch written on it, and the oval's got 6-inch written on it. Well, guess what? They ain't the same thing. Now you can pay Echo to stomp on that duct, or you can stomp on it yourself, whatever you choose, but the net result is the duct is exactly the same. It carries the same label, but they don't do the same job. In fact, if you look at the science of it, our 28 square inches round duct becomes 21 square inches when it's flattened. But that doesn't tell the whole story, because aerodynamically the best duct you can buy is a round one, because it encloses the most square inches for the least friction surfaces, which is the perimeter sheet metal. So by the time you take that consideration into as well with the dead ends of that oval, you've ended up with a 6-inch duct becoming a 5-inch duct, but it's still labeled as a 6-inch duct. It's being installed as a 6-inch duct as an equivalent, but the only equivalency between the two, excuse me, is the weight. Now, just as looking things backwards, it'll absolutely blow you away. But if, for instance, I had a 5-inch duct in a house, and I decide to upgrade that branch run to 6, I have a 66% improvement in the performance of that duct. 66% more airflow. When you consider all of the physics behind it, these are real, solid numbers of the gain in just that one size. Okay, now let's look at the next step. The study, however, which cost about $11,000 and took Don McAdam an entire summer and an entire pickup truck full of sheet metal from Loris Krish at Echo, we wanted to compare the best way to get to Mrs. Smith's bedroom from a crawl space or basement ceiling, which was to go up the partition wall and use an 8-foot riser or a 10-foot or whatever it is with elbows, because elbows are the lowest cost, smoothest flow fitting that we can use on a round duct. And the net result is that in that situation, if you have a 6-inch duct, 6-inch 90, 6-inch 90, 2 or 3 feet of straightening, 8 or 10 feet of riser and elbow, 2 or 3 feet, the mathematics of it is 34 equivalent feet. In this case, each of these elbows is worth about 10 lineal feet of equivalency in terms of the pressure loss in pushing air through that thing. But this ain't nothing. Don McAdam took these 16 different methods which were brought to us by the installing trade. He laid them on a table with absolute precision over an entire summer, actually measured each of these things. And unlike most reports, what we did, I'll get there in a minute, we summarized his entire summer work, not in 100 pages of crap to feed the PC housing, but 1 page. Drawings occupied half of it, and the text occupied the rest. What we used to do 30 years ago, before we cost cut ourselves into the toilet, is we used to use 3x10 duct, which is pretty good. That was 41 feet of equivalent length. But it did allow us to fit within the constraint of a 2x4 wall, although it occupied 10 inches of plate instead of this oval, which is 8 inches of plate. But it did do a reasonably good job at 41 feet, which isn't a whole lot of a penalty over the theoretical ideal of using the 6-inch riser. Now this is a pig in that this 6-inch duct now is 149 feet, because we have an effect of a 5-inch duct here and horribly unaerodynamic fittings here, which I should be pointing out, these fittings are made at lowest cost, lowest amount of metal content, because there are no standards to which these are made. These are made by any different manufacturer, all the different methods, and this was the lowest cost way ECHO could produce this, so it's the lowest cost fitting. But the net result is we have 5 times the pressure loss, and therefore 5 times the pressure force to get air through it than what we've had before. It's just complete circus. And you see this everywhere. It's just a disgrace. And we're going to soon find out when houses get tighter that we're not adequately heating and cooling the top floor, because the simple numbers of turns of direction it takes to get from the appliance to Mrs. Smith's bedroom. So believe it or not, that page is $11,000. Within about a week of it being produced, that went onto ECHO's website, because we're happy as hell to be able to produce legitimate, technical, supportable, documented information on the performance of it. So there's, I think, 10 drawings there, and there's a number of multiples of each of those choices. But you can look at them all now, and I've showed you the best and the worst, and yet they're being installed as though they're equivalent. So not only do we have bad fittings, up till now I've ignored duct leakage. And duct leakage, in our own experience, we have done 750 tests on single-family dwellings and some multiples hotels of small ventilation systems just to find out what the leakage rates are, and we're running anywhere from 10 to 50% leakage. So again, if you're ending up trying to get air to Mrs. Smith's bedroom, not only are the fittings restricting the air that we get there, but if we don't really seal things up, which are now, as a requirement, is at 936, 937, the energy section, the sealing of the supply ducts are called for, but so often you get stuff sealed that you can see, but you won't get any of the backside sealed. And I didn't bring one here, but if you have a 6-inch elbow, it's got 3 adjustable doors. These little swivel things are called doors. And they're beautiful things because you can make them 45 straight wherever you want. If you take a 6-inch one of these guys, and you got 3 gores, and you got a joint in either end, there's 96 inches of joint length in the use of this one fitting. And it's real common in ventilation to have a box of maybe 20, 30, or 40 of these going to a house. So you can imagine what's happening for duct leakage contributions. It's just a disgrace. You know, here's a long radius elbow, properly sealed. I mean, this is well done. Seldom you can do it because you seldom have an open truss like this, but it makes a difference. The conventional answer in Canada, we don't care, because our duct, by and large, is in conditioned space. So the age-old thing we get from NRC for the last 50 years, and I should admit, after sitting on Part 6 for about 5 years, 20 years ago, before I gave up and discussed, NRC has no capability mechanical. They're a building enclosure-centric organization, and the expertise in mechanical does not exist. But the philosophy in Canada is leakage doesn't matter. And it doesn't really matter what we do if the duct is in conditioned space, because the loss from it will be into conditioned space. Well, this blows up on our face if we start to right-sizing it. We start to want to get the proper number of BTUs in Mrs. Smith's bedroom, and losing 20 or 30% of it en route ain't going to cut it if we start sizing correctly. Real leakage does matter if you right-size equipment. You care about heating specific rooms, cooling, or ventilating specific rooms. This is a small little demo, and I hope I can make this thing work. I think I maybe can with the computer. Should. I can do it in reduced form here. Just a second. Where the hell did my mouse go? Do you see my mouse rolling around? Where am I? Oh, okay. It's on your screen, but not mine. Thank you. Oh, crap. That's a skill that I don't have. Okay, just to explain. Some years ago, we bought a theatrical smoke generator. It's been a hell of a lot of fun. What we have is a small fan, a smoke generator just off screen. We got air going through a flex duct into an upside-down brake pan that's been sealed and sitting in a garbage can. And we have a regular 6-inch elbow above it, capped at the end, and a Mickey Mouse masking tape job at the bottom, foil tape at the top, so that we were exposing the air to 3 cores worth of leakage. I probably personally tested 200 houses using this, and when you get a leaky system, smoke descends up all over the place. We had a few people panic and want to call the fire department. We used to use smoke bombs, and that did freak everyone out because you can't stop it once you start them. This thing's a lot easier to pull the plug if you get desperate. But the bottom line is, this is quite illustrative to the trade, and they're absolutely blown away when they see it for the first time, because in Canada, we've never, ever questioned adequacy of duct in a system before. And we've been getting away with it because we've had cheap electricity, we've had forgiving appliances that run at very high temperature rise, so they're becoming forgiving simply because they tolerate this restriction because they can take the high temperature. Those days are gone, and if we do move as a province toward heat pumps, this is going to blow up in our face, and it's going to hurt us real badly. Okay, I think that's just about it. Yeah, that's a smoke generator. It's a lot of fun. Is anyone here from Township of Langley? You had a lady organize an open house out here in Fort Langley a while ago. We took this out here. It was quite a demonstrator. It was about 100 builder developers, and I certainly dropped them in their ass. First year guidelines. The first year guidelines, like our ventilation guidelines, is a prescriptive standard, and it was written 25 years ago by friends of mine, Paul Villacourt and Doug Harwood. Doug Harwood is a professional engineer, very highly respected, and this was written to be an inspectable standard. So what I said today directly supports the ventilation guidelines, it supports the first year guidelines, but are an attempt to give you a little bit of background on what's behind those standards. That's all there is. I'm welcome to questions. We're a little bit early. Anything off the table, anything mechanical. I'm just a nerd for this stuff. I love it. If I can help you, my job is to help that.
Some of the systems I see that the guys are sealing all of their 90s and holes and around the furnace area, and then the seams on their piping. They're sealing the fittings, but they're not sealing the piping seam.
Are you referring to what's called a snap lock?
Yeah. Yeah. Does that have to be sealed as well?
For those of you who don't know, this is round pipe, sometimes called duct, sometimes called pipe. It's shipped nested because it's compact, and these joints are snap lock. The 4-inch one's very hard to get apart, but they're shipped as a sort of like a letter C, and they nest 10 together in 36 and 60-inch lengths. The question that's asked, does the snap lock leak? And in our own personal testing, we found that some brands do, some brands don't. So we as universities say seal it, because it's the least labor component of it. And when I speak about sealing, I'd like to be very careful with the choice of words. Painting is different than sealing. Painting is when you're trying to cover area. Here you're not trying to cover area. When you brush on sealant, you have to brush it against the open, sharp edge. And you don't just paint it around to look good, you actually have to paint it into the gore. But whether you use a duct sealant mastic or whether you use foil tape, which has acrylic adhesive, it doesn't matter, they both really, really work well. But the duct tape is a joke because in Canada, its standard is fire and flame spread and smoke developed, and there's no reference to longevity in the standard. So it's good for taping busted windows and fixing your shoes if the sole falls off.
Can you speak to using joist space and stud space openings as cold air repair?
I'm going to dodge your question from the point of view of code, but deal with it practically. The question that comes up, what do I think about using a joist space for cold air return? What I'm seeing happening right now is, in simple form, we should look houses as more or less non-compartmentalized. We're building a better enclosure. The interior partitions leak like hell because we don't really care about sealing. So we basically have a non-compartmentalized enclosure, albeit with doors, they still have a half-inch undercut. In my opinion, what I've learned in the last 40 years is the point of return is far, far, far less critical than ample return. Failings, for example, comes from the old school where the thinking was be always go gross on return. And that's a good concept because if you give the appliance all the air it wants, it leaves more available static pressure to overcome a filter and that of your supply distribution. So freeing up the return aids you in getting the air to Mrs. Smith's bedroom. So from the point of view of whether the return leaks like hail or whatever, I don't care that much personally. But I'll dodge the code section because I'm not involved with 933. Jenny, do you have any comments on that?
No.
Yes, Jenny. Okay.
I do not. I'm not up on my 933.
Either am I. That's another committee within Tech that looks after that. Any other questions from any angle here? I'm here to help you, personally and professionally. Yes, sir.
Paul, City of Burnaby, having looking at your demonstration, it's all we're going to require air pressurization tests on houses and stuff, and it's almost like worthwhile to say, well, why don't we mandate something in duct work too, where you throw the smoke bomb in there and see how it works. But it's pretty hard to measure though.
The question is what would be a first step for doing something with inspection of heating? I think we have to recognize that we have a very difficult job in Canada, is we do not have this expertise at the research level. So we have to decide what is the very simplest baby steps we can implement at the moment. I believe what we should be doing right now is forgetting a lot of this finesse. We should be looking at really brute force stupidities. And that's what's killing us right now. It's not these little wee things. We've got to look at big things. For example, I was out in Squamish doing this course about 2 weeks ago, and I heard of a 4-ton piece of equipment going with 2 8-inch round ducts for return. What we have to do is we have to have tables in front of us, supply tables, return tables, and at least look for minimum duct sizing based on those tables, based on the CFM of that appliance. Because the manufacturers would support it. These manufacturers aren't stupid. They protect themselves with requiring a temperature rise and a certain external static pressure. We're exceeding those on many, many installations. So prescriptively, the easiest answer is go in there and measure square inches on return, go in and measure square inches on supply, and that would be the first step because it's so damn freaking easy. You can do it with a tape measure in 5 minutes. And you're probably going to kick 75% of the biggies out of the ballpark. We can go from there, but that's far, far, far more basic than our forced air guidelines, which has prescriptive steps if you want to go further. But as a beginning step, look for square inches. Are any of you old enough to know the Blue Flame Standard? Okay, Blue Flame Standard was written by BC Gas, which was BC Hydro 30 years ago, and it had minimum square inches that you needed for return and supply. It was beautiful, simple, enforceable. And that's where we have to go as a baby step towards proper HVAC inspection.
With regard to your comments about measuring the return area and the supply or cross sections, are they supposed to be equal? I gotta know that.
No.
I'm sure they don't have to put one package to begin it, right?
When I look at a fan, this fan is better because this is ducted on the return and the supply. I could not answer your question looking at the bath fan. This fan does not care if it pushes hard or pulls hard. It sees that some of the two works. So when we teach it, we always teach it. The most economic answer was to split that pull and push to be equal. But if I was doing a house right now for myself, I'd make the pull real easy to give me all sorts of pressure available for a filter, and they have lots of push so that I get into the far corners of my house. Because that's what Mrs. Smith is always pissed about. We can't get enough air to her back bedroom. And that problem is created by two things. Too small and too many changes of direction on this, but it's equally caused by an overly restrictive return because all of the capability of the fan is used here when it should have been used where we have less difficulty. Sorry, we have more difficulty in finding square inches to do the job.
Right. So my sister did a renovation last year, and she's got an older house. She's put a new furnace in. I'm going to go over and take a look at her house. When I get back, and I'm going to look for that right angle turn at this bottom side.
I'll tell you, it will be right angle, but if you tell me who installed it, I can tell you exactly how well it's done. Who did it?
Oh, this is in Okanagan. So.
Oh, no problem. Who did it?
It wasn't me. But yeah, I don't know who did. But what I'm wondering is, as an inspector, whether it's from my sister's property or from my own or from my work, I'm going to go in there and take a rough look at these systems, and I see a 16 by 8 return air, and I see 4 8s coming off the
what I should do is I'll quote you the blue frame standard from about 30 years ago, because that's the only one I can do right off the top of my head. It was a 100,000 BTU furnace, you need 200 square inches for return. Now that doesn't apply today, but that's the kind of thinking you have to do. In the Quality First manual, which I don't teach, I'm not involved with, we have tables for return and tables for supply. Call up Catherine, ask for the tables for minimum return and minimum supply for Quality First, and it will give you those sizes and square inches. That becomes an easy first step. Yes, Jenny?
David, I don't know if you talked about this because I missed the beginning qualities, but the TECA Quality First guidelines were added into 933, I think a couple of years ago as a reference. So I don't know if everyone's aware of that, but what it says is if it's an aspect of the system not specifically covered by the code, then you can use those TECA Quality First guidelines.
Okay, just to summarize what Jenny has said, TECA is referred under 933. So one would argue then, since it is referenced, one could say you would then, correct me if I'm wrong, have the legal clout to enforce the minimums of those two tables I've referred to.
Yeah, so it's one of the options, right? It says if there's aspects not specifically covered by 933, you got to install to good practice. And then the guideline, the TECA Quality First stuff is one of those examples. So people could be using other, I think there's HRRAI stuff. There's other options, yeah, but this is one of them.
Anything about that table is prescriptive, which of course is the only method by where you're going to tell if this works, because the only time you can inspect this is a rough-in. Any time later is just a waste of time. All you do is say, yeah, it's no good and you can't fix it, you're screwed.
Question. Walk on site, looking at mechanical, is there anything that contractor you never can say I'm certified to do this work?
Well, we have a little bit of a problem right now. We developed a CHT program, Certified Heating Technician Program. It had three facets, geo, air, and water. Right now it's a chicken and egg. We haven't been able to sell it. We have 100 people through it, but no more want to take it, commit themselves to the training because it's not required. So we've got a bit of a pickle in that regard. At the moment right now, if I was hiring for someone to do heating, I'd hire a red seal sheet metal tradesman because that's the only sort of designation that I can hire on the street today. He's been through the 4-year apprenticeship program. But one of the dilemmas is that program doesn't do squat for residential heating. So a guy really needs to have a red seal program, in my opinion, and the Quality First, all the air courses. And what we are doing at TECA is we're going to put, and this is just at the board level right now, is we're going to introduce this concept of a forced air heating ventilating designer, and that would require him passing and going through the forced air guidelines, the ventilation, this promo course, the HRV course, all the airside courses, and he will get an additional stamp that will certify his having been through all four. So that's our stopgap position until such times we get the CHT in progress.
The reason I first took these courses in '97, and I haven't attended one of these in a while, but when you say a square boot coming in, it's like, what? It's the definition of insanity in our industry. We tried, we're doing the same thing and expecting a different result.
I think Einstein said something about that, didn't he?
Yeah, and it's the aspect of why are we looking for more certification? Again, I go back to the Building Act, we have to show the threshold designation, to look at homes, to look at bigger homes or commercial, and then the complex stuff, we have 3 levels. I find it so hard to see the amount of monies they're spending trying to improve our knowledge, but you go on, you see these horrendously sloppy jobs, and then you have to start battling individual people. I just wish, again, people in the province would see that some certification standards.
Well, as I told you, I'm getting old, senile, and cynical. The answer I have is real simple. We are losing people from our industry because they can't compete with those that are at the low end. If we really want to bring about change, well, our business is training. That's not the issue. The issue is we have to give you the confidence to kick the living shit out of guys who are incompetent and dragging the industry down with fraudulent or non-working systems. And that's why all we can do is do everything we can to help you politically and technically at least kick out of this industry the ones that are disgracing us the most. We just went through legal here about a month ago to go through the process of suspending certification of ventilation And I suspect that we're going to be swinging that door open and close an awful lot over the next year. It has to happen. Yes, Jimmy?
Since we're pointing fingers at the province, I feel compelled to.
That was really subtle. Well, they're the controllers, right? Building that.
We are not the controllers of that particular issue. So the only trades we regulate in the building code is plumbing.
No, I'm saying the province.
Yeah. So and it's not the Building Act either, though, right? So you're right. There are people in the province that deal with this. I think there's some work happening with regulated trades. I don't think it includes stuff like this. But those industry, like the industry training people, they've been through a rough ride over the last 20 years or so, right? There was a lot of control over trades at one point, and at one point I think they really just almost shut that part of government down, and I think they're trying to build it back up again. So I think hopefully we'll see some of that, some progress there, but it wouldn't come from our office.
There be opportunities for limiting the amount of energy per cubic foot or per square foot of house that could be dedicated towards air handling. And like this seems to be a pretty major issue in terms of the true cost of running these systems.
Well, basically, the energy to do this is all the electricity to move the air. And at the moment, I don't believe there's anything in legislation in 930, is it 936? That governs that? It's certainly not in 933. If you want to have a real laugh, here's what's stupid. When I rate my gas furnace at 95%, guess how the game's played? All the electricity that went in to move the air is actually raising the efficiency of that appliance. So it behooves me to have the worst motor I can put into that device, because the electricity used makes the gas efficiency look better, because the two outputs are additive to raising that efficiency. I mean, there's stupidity in that, just choke a horse. Also, what you don't know is these efficiency ratings on the appliance are running at the lowest temperature rise, because that's how you extract the most heat. Well, it's not a hope in hell you get duct picking in a real world to achieve those numbers. So this whole thing is smoke and mirrors. The whole thing's a game. We're gaming the system. Let's go back to simple shit and do simple things right. And we embrace your support anybody can offer. I think I'm expired. What time is it? You guys have had enough for me. Thanks very much for being here.